In the past couple lectures, we talked about Riemann sums and definite integrals, and I wanted to do another example from the packet. So looking at Riemann sums, recall that we can use rectangles to approximate the area under the curve by subdividing the period that we care about the area for into subintervals, where, using n equal 5, n equal 10, depending on that. And one of the things we talked about in class is that the more subintervals that you use, the more accurate it will be for the approximation of the area. Meaning, just because the amount of extra that's left off, or the amount of area that is too much that is being calculated by those rectangles, will be reduced. But last time we figured out the Riemann sum to approximate the area under this parabola from 0 to 5. And then we talked quite a bit about definite integrals and how those help us find the exact area underneath the curve. Or again, if we're looking at the definition, it says let y be equal to f of x be continuous and non-negative over an interval a b. A definite integral is the limit as n approaches infinity of the Riemann sum of the area of rectangles onto the graph of the function. Or as I was saying, if you can imagine taking an infinite number of little mini rectangles and adding up all of those, there would be virtually no error and it would give us a precise area. And again, one of the ways we could write that is the limit as delta x approaches infinity, or it's usually written, or the limit as delta x approaches 0, or the limit as n approaches infinity, equivalently, of the sum of all of those areas. Remember, because the areas are always calculated by the width, which is delta x, times the height, which is determined by the function. And also, kind of as I said in class, the limit as n approaches infinity, this is sort of what we think of as an integral symbol representing, is sort of obviously a simplified version of that, because as we can all agree, that is a pretty complicated expression. And then delta x on the infinitesimal level, just we change to dx. So that's, again, what this means. And when we write a and b, that is signifying the interval in which we're finding the exact area under the curve. Because, again, the area is given by that some infinite number of little rectangles to sort of span the area under the curve in that period of window. And, as we talked about, the antiderivative function is sometimes called the area function. And that's why a definite integral, taking an antiderivative helps us find the area. But again, as a definite integral is defined, is capital F of b minus capital F of a. Or in other words, take the antiderivative of the function evaluated at b and evaluated a, and take the difference of those two things. So let's actually take the previous example and find the exact area underneath the curve on this particular interval. So we found an approximation to the area based on the Riemann sum, which was 40. And what we should expect is that the exact area should be fairly close to that Riemann sum. And again, what we would be calculating is a precise area, which takes into account, not using rectangles or triangles or other geometric figures, precisely the perfect curvature and all of the area underneath it. And you can imagine how this could be very important, say for manufacturing. Say we were trying to we're an engineer or something, and we're trying to create an object with this shape out of metal or whatever. We want to know how much material is it, how expensive is it going to be, those sorts of things. Knowing the area could be relevant in that particular context. And again, we'll talk more about applications of integration later. But basically, as I was saying, we could take the definite integral of the function with respect to x. And again, this is kind of a representation of I'm taking an infinite sum of subrectangles with respect to the x-axis. And the function itself is on the inside. And again, this would be called an indefinite integral, which would give me the antiderivative function, which again would be a function which determines the area from 0 to x. But if we just use if we write from a to b, 0 to 5, on our integral symbol, again, this is now we call it definite integral, and this means that we're trying to solve the area in this interval from 0 to 5, always underneath the curve. Assuming it's above the x-axis. And if it's below, it still works, but we'll talk about that more later. But anyways, as we talked about in class, we did a couple examples, and I wanted to do a few more. We always want to start by finding, well, what is capital F, and then plugging it in. So how I like to write it is solve my antiderivative function. So the antiderivative of x is x squared over 2. And the antiderivative of x squared is x cubed over 3. Because remember, with polynomials, we want to add 1 to the power and drop the reciprocal. And remember, we do not need plus c when we are doing definite integrals, because it will, even if you were to use it, it would cancel anyways. And how I like to write it is from 5 to 0. And again, what we're signifying is here's my antiderivative function, and I need to plug in both 5 and 0, b minus a, and subtract the 2. So if I start by plugging in 5, I would have 10 times 5 squared over 2 minus 2 times 5 cubed over 3. And then minus the function evaluated at 0. Well, what's nice is since these are just polynomials, I would have 0 and 0. So minus 0, I can not worry about that. But be careful with 0 because, not all functions would it actually make 0. But in this case, it kind of skip the 0 point because it ends up making 0. And really, the antiderivative function gives you the area up until a particular point starting at 0. So usually they do start at 0. Anyways. But let's go ahead and clean this up. So what this would give us is 10 over 2 is 5 times 25 is 125. And then this is minus 2/3 times 125. So since that's 125 minus 2/3 of itself, that should just leave us with 1/3 of 125, or 125 over 3, which is not divisible, and that's good enough. We could actually approximate, what is that? 125 divided by 3 using a decimal is going to be approximately 41.6, or exactly 41.6 repeating, but approximately 41.7, which again would give us the exact area under the curve. Technically, that is an approximation to the exact number. The exact number, if we left it as a fraction, that would be the exact area under the curve. So, but you can always take the exact area and round it off, and that's good enough. But just be careful if it says exact area. Might want you in say for example the online homework, it might want you to enter it in as a fraction instead. And notice it's very close to the Riemann sum answer we got, 40, which was an approximation. And again, if you were to divide it up into 10 or 20 or 30 subintervals, what you'll see is it will actually get closer and closer and closer. So we started working on this one in class, but didn't finish it because we had a lot to cover. But try it on your own and see. My guess is you'll get something more like 41. And if you keep increasing the number of subintervals, what will happen is it will get closer and closer, which explains why the limit as n approaches infinity of the Riemann sum gives us the integral. But as you can probably agree, it's much easier to use calculus, meaning apply the antiderivative, apply the definition of a definite integral to solve for the exact area underneath the curve.